Okay, so let's start. So we're looking at some basics of real analysis in the last class, where we recalled like simple notions such as lower bounds and upper bounds, what is a supremum and infimum of the set, and we also looked at what countable and uncountable sets are, and basics of functions. Right, and towards the end we looked at what is a metric and how do you define a norm on a particular vector space, right? It's always good to keep in mind that a metric can be defined on any set, right? Whereas for the norm you should note that it requires some vector space structure, because you need the notion of scaling of a vector for this particular statement to make sense, and also you should also have a unique zero vector. Correct? So for a metric you just need an arbitrary set, and any function that satisfies all of these properties is a metric. Right? So any questions from the previous class? Okay, let's continue. Just as we've defined the norm, we can also define inner products for two vectors. So given any two vectors, so let's suppose that F is some vector space. Then any function that operates on pairs of vectors and outputs a real number is called an inner product. If it satisfies all of these properties. So firstly, we want to think of this as the dot product between two vectors. What's the most basic property that we can think of? Symmetry, right? So if I take the inner product between x and y, this should be equal to the inner product between y and x. Okay, what else? What other properties does the standard dot product satisfy? Yeah? Correct. So the product with itself should be the norm square. Well, it's not necessarily tied to a norm. So what property should that satisfy? Okay, something even more basic. Yeah, it should be non-negative. In particular, it should be positive for all non-zero vectors. So F, the inner product of a vector with itself should be greater than or equal to 0 for all x, and equality holds only if x is the zero vector. So that's a basic property that we require. The third property that we'll require is some form of linearity. In particular, linearity in one of the arguments. If I take f of alpha x1 plus beta x2 along with some vector y, then this should be equal to alpha times the inner product between x1 and y plus beta times the inner product between x2 and y. So as long as I have some function that operates on pairs of vectors and satisfies these properties, it is an inner product. It's a valid inner product. So the standard example of the inner product that you've seen is just the dot product. Right? So As an example, f of xy equal to summation I equal to 1 to n xi yi. This is a valid inner product. Okay. Can you think of some modification of this particular inner product? Now suppose instead of taking summation xi yi, I add some kind of a positive weight to each of these entries. Okay, so I'll fix some set of real numbers. Let's take an example. Let's look at R2. So let us consider an inner product on R2. I'll say that the inner product between x and y equal to 2x1 y1 plus 3 x2 y2. Okay, I've defined a function over here. Does this satisfy all the properties of the inner product? Is it symmetric? It is symmetric. What about the second property? Is it always is the inner product of a vector with itself always positive for non-zero vectors? It is, right? And if I take inner product of the zero vector with itself, it is equal to 0. So the second property is also satisfied. Right? So the second property is satisfied. What about the third property? Is it linear in the first argument? It is, right? In fact, if you look at this as a function of just the first argument, then you can write this as 2y1 3y2 inner product with x1 x2, right? So this is a linear transformation of x1 x2 and therefore is linear in x1 in the vector x. Okay. So this is a valid inner product. Okay, so as we saw, this is a valid inner product. Right? Now suppose instead of taking positive weights on each of these entries, what if I took negative weights? Let's say f of x1 comma f of x comma y equals 2x1 y1 minus 3x2 y2. Is this an inner product? Why not? The second property is not satisfied, right? For example, if I take the vector 0 comma 1, then the inner product of that with itself is not positive. So this is not an inner product. So here's a homework for you, pretty simple. So show that in any dimension Rn, if I look at the following function f of x comma y equals x transpose ay, this is an inner product if is positive semi-definiteness enough? Okay, symmetric, yes, symmetric, and has to be symmetric and positive definite. Yes, positive definite. It is not. That's the whole point. Okay, can you give me an example, a simple example of a matrix which is positive semi-definite but not positive definite? Take the all zeros matrix, in fact. Is that positive semi-definite? Yes, it's not positive definite. But would that constitute an inner product? X transpose ay, which is always equal to 0 for all vectors. Correct. So you essentially want this property to be satisfied, right? So equality, the inner product of a vector with itself should be strictly greater than 0 if x is non-zero. Okay, and that property is violated if you just take x to be positive semi-definite, because you can always find a non-zero vector for which x transpose ax is equal to 0. Okay. Any questions? Okay. So now let's look at sequences. So how do we formally define a sequence on, let's say, the real numbers? So sequence on, let us say, a set of real numbers is, you can think of it as a mapping from 1, 2, 3, so on, a set of natural numbers to the set of real numbers. So f of I is just the ith element in the sequence. Of course, the sequences on real numbers are not all that are interesting. Where we're interested in, let's say, sequences of vectors or sequences of matrices, correct? And if I have a given sequence on any set, I can define a sequence on any set. Just a collection, it's an infinite collection of elements from that particular set, correct? And there is some particular order to this. So if I have any sequence on any metric space, so take any set and let's define a metric on this particular set. Then we say that this sequence, let's call this x1, x2, and so on. We say that this converges to a limit if what happens? Can you? Yeah. Okay, correct. But how do we define that? Okay, let's say let's give an epsilon and delta.
But if the epsilon greater than 0, there exists a delta
Okay.
such that mod of x and minus x is less than.
Okay, so let's try to think about it more intuitively, right? What should happen? Suppose that the sequence converges. So take a sequence of real numbers. Okay, pick something, say 1 by 2 to the power n. Okay, what does this converge to? 0, right? So what should happen if when we say that this sequence converges to a limit? It should be the case that if I take any small epsilon from 0, for all sufficiently large n, all the values should be close to 0. Correct? And no matter how small I make this epsilon, beyond a certain point, all the values should be close to this, to the limit. Correct? So let's put that down formally. So we say that the sequence converges to a limit x if for every tolerance right, we can find some n such that all the values of the sequence beyond the nth value, all of them lie close to epsilon close to x. Okay, and this can be any distance. Now it's just because I define a sequence on some particular set, it doesn't mean that it has to have a limit just because it need not converge to a limit within that particular set. For example, let's consider the set, the open interval from 0 to 1. All right. If I look at the sequence, xn equal to 1 by 2 to the power n. All of these elements lie in this particular set. Do you agree? But does this converge to an element within this particular set? It converges to 0, which doesn't lie in this particular set. All right. And this distinction is important. Okay. So for what kinds of sets do sequences always converge to an element within the set? So that in fact turns out to be the set. So if every sequence of elements taken from that set also converges to an element in that particular set, then that set is closed. And in fact, we'll treat that as a definition of closed sets. In fact, that's not the correct definition, but those seem to turn out to be equivalent, at least for our purposes. So if you take any sequence of elements from A, which is convergent, then this will always converge to another element of A. So for example, let's take the closed interval from 0 to 1. Is it possible to construct a sequence of elements from the closed interval 0 to 1 and still have the sequence converge to something which is outside this closed interval? As it turns out, it's not possible. Okay, so let's take some more non-trivial examples. Consider a finite set. Let's say 1, 2, 5, 10. So this is a finite set, and suppose I take any sequence, an infinite sequence of elements from this particular set. Can this converge to something outside this particular set? So if I take any convergent sequence of elements from this set A, what would it look like? All the elements? Okay, but does that have to happen? Do all of the elements have to be the same? Correct. So if correct. So if you take any infinite sequence of elements of A and that is convergent, then the only possibility is that beyond a certain point, all the elements repeat. If they do not, then by definition, it won't be convergent. So for example, let's suppose that I have an infinite sequence of ones, but after every 100th element, it's a 2. Okay, so let's take xn equal to 1 if n is not, or let's say n does not divide 100, and 2 if, sorry, I should put it the other way around. If 100 does not divide n, So if n is a multiple of 100, then it's equal to 2. And if it's not a multiple of 100, then it's equal to 1. Right? So the 100th element is equal to 2, the 200th element is equal to 2, the 300th element is equal to 2, and so on. But all of the other elements are equal to 1. Is this a convergent sequence? It doesn't converge to anything. Correct? So if you have a convergent sequence of elements from this set, then all of them should be identical beyond a certain point. So this set is in fact closed. In fact, you can use a similar argument to show that every finite set is closed. Every finite subset of Rn is closed. Let's take another example. The set of all rational numbers. Is the set of all rational numbers closed? How many think that the set of all rational numbers is closed? Okay, how many think that it is not closed? Okay, I need a proof or a counter example.
If you say that if it's not closed, then it should converge to a point outside the set of rationals.
Correct.
So complement which is irrational.
Okay, yeah.
So if it converges, but I know that between rational and irrational, I'll be able to then again find another rational, which would mean that again belongs to a set of rationals. So it should then
Should it? So take any arbitrary irrational number. Okay. Look, let xn be the first n digits in the decimal representation of that irrational number. Does this converge? Or let's take another example. This is a sequence that you have seen, a limit that you have seen in your high school. Take xn equals 1 plus 1 by n whole to the power n. What is limit of xn as n tends to infinity? It's equal to e, right? And is e rational? It's not, right? It's a transcendental number. It's neither rational nor irrational. So the limit of this particular sequence is not a rational number. But for every n, is xn a rational number? It is, right? It's simply n plus 1 by n whole raised to the n. N plus 1 by n is a rational number, and product of any n rational numbers is also a rational number. Correct? So this converges to E, which is not in the set of rational numbers. So Q is in fact not closed. Right? So in fact, it turns out that the smallest closed set containing Q is the set of real numbers. So in other words, if you want to complete Q, by looking at all possible limits of sequences in Q, you get the set of real numbers. So now that we've defined a closed set, let's try to define what an open set is. Okay, so to define an open set, I need the notion of a neighborhood or an open neighborhood. So I'll define B of X. So take any point X, the open neighborhood of radius epsilon around X so this is a notation that I will use to denote the open neighborhood of radius epsilon around a point X. Again, think about it intuitively. What should an open neighborhood be? Set of all points within distance epsilon to X. So it is the set of all points Y in your set such that the distance between X and Y is strictly less than epsilon. Okay, it's important to have this strictly less than epsilon. It's not less than or equal to epsilon, it's less than epsilon. So if you think about Rn and the standard Euclidean distance, then it's basically the open ball around X. So you take the ball, but everything except the surface. Okay, and that constitutes this open neighborhood. And I'll say that a set is open if no matter which point I take from this particular set, there is always room to be within the set. Okay, so if you think about the open interval from 0 to 1, you pick any point. Okay, on either side, you can always move a little bit, a distance of epsilon around it, and still be within the set. So contrast this with the closed interval 0 to 1. If I take the point 1 or the point 0, I can't move any more to the right and still be in this particular set. But if I take the open interval, you pick any point in this open interval, you can be arbitrarily close to 1, but there's always, you can move a little bit to the right and still be within this particular set. Okay, so that's the intuitive interpretation of what an open set should be like. So a set is open if no matter which point you pick from this particular set, I can always find some epsilon such that the open neighborhood of radius epsilon around X is contained in the set S. Okay. Again, this is just a definition, and let's see some examples. Again, the open interval from 0 to 1 is obviously open. every open ball is also open. Every neighborhood is open. What about the set of all real numbers? This is also open. Do you agree? You take any point in R. Can I have a neighborhood around that particular point which is also in R? Yes. Right? Yeah? I'll come to that in just a minute. Okay. So, in fact, the complement of a closed set is open. So, for example, let us take the closed interval from 0 to 1 and take the complement. This is minus infinity to 0, union 1 to infinity. This is an open set. But there are more interesting examples, for example, such as say 1, 2, 3, a finite set which is closed. I take the complement. This is also open. Because this would be a union of the following intervals: minus infinity to 1, union 1 to 2, union 2 to 3, union 3 to infinity. So in fact, the union of open intervals, the union of open sets also happens to be open.
Complement of an open set.
In fact, the complement of an open set is closed.
Take open 0.
Sorry?
Take open 0.
Yeah.
Complement is minus infinity, including 0.
Correct. So I'll come to that point in just a minute. This is open, and it also turns out that, okay, let me come to that later. Let's again go back to the example of real numbers. Okay, so set of all real numbers is open, correct? But is it closed? Take any sequence of any convergent sequence of real numbers. Is it going to be a real number? Yes. So in fact, the set of real numbers is both open and closed. So a set, if it is open, it doesn't necessarily mean that it is not closed. So there can be sets which are open but not closed, closed but not open, both open and closed, and neither open nor closed. All of these are perfectly possible. The complement of an open set is closed. So if you take the complement of the open interval 0 to 1, this is equal to minus infinity to 1 union, sorry, minus infinity to 0 union 1 to plus infinity, and this is closed. Now, I'm making many of these statements without giving formal proofs, but we're not going to cover that. I can only point you to references because going through all of these proofs would take an entire semester itself. Okay, so this is something that you would see in a first course on real analysis, which is also being offered by the math department. But for us, we need to know these definitions, and we need to have a good intuition as to how to use these definitions. Okay, because all of these notions, open, closed, and as we'll see later, compact, these turn out to give sufficient conditions for which optimality can be guaranteed. So suppose I give you an arbitrary function subject to some set of constraints. I give you an optimization problem. Does this have a solution? Right? That's the first question that we want to answer. For what kind of constraints is a solution always guaranteed? That is, a maximum or a minimum always exists. Okay? We'll see that if the constraints correspond to a set that is closed and bounded, and the function is continuous, then this will always have this constrained optimization problem. Will always have a maximum and a minimum. Okay, just these three properties are sufficient. The function being continuous, the set being closed, and the set being bounded. Okay. But in order to ensure that it has a maximum and a minimum, we need to be able to verify whether a function is continuous, whether the given set of constraints corresponds to a closed set, and whether it is bounded. Yes?
So can a set be neither closed nor open?
It can be neither closed nor open. I mean, simplest example is open on one side and closed on the other. So this set is neither open nor closed. Okay, so that's again, it's hard to verify whether an empty set satisfies either of these properties, correct? Because what do you mean by a neighborhood around the empty in the empty set? So all we can do is use some of these properties. The complement of a closed set should be open, and the complement of an open set is closed. So what is the empty set? You can think of it as a complement of the set of all real numbers. So the set of all real numbers is both closed and open. So the empty set is both closed and open. But this is really just by definition. It is one of those sets which is not particularly interesting, but it's still one of those corner cases that we have to take care of. Any questions? Yeah.
While defining sequence, it told that equation R is mapping from real numbers to R.
So sequence is basically, you can think of it as a mapping.
Any sequence or
Any sequence.
any random sequence can
It is a valid sequence, correct? But then it doesn't mean that it converges to anything. So it is just a function from the set of natural numbers to a set of real numbers. That's a definition of a sequence, correct? And this, you can think of this as the index of the sequence, right? So 1, 2, 3. So f of 1 is the first element in the sequence, f of 2 is the second element in the sequence, f of 3 is the third element in the sequence, and so on. Just that. Is that okay? Any other questions? Yeah.
So here when we are talking about sets, we mean real sets.
It could be any set.
So can it include complex numbers?
In principle, I could define all of this over the set of complex numbers as well.
So the definitions might change for the. So like we are saying now that real number is both open and closed.
Correct.
But if we also include complex numbers, then that thing might change.
Which thing? So again, when you say sequences, or so you first always have a space which you can think of as your universal space. So over this you need a metric. Okay. So for example, it could be the set of all complex numbers with the standard distance between. So how do you define a distance on complex numbers?
Like we're taking the norms.
Correct. So the modulus of the difference between two numbers gives the distance between those two numbers, right? Okay. So now that you have a metric and you have a space, you have a metric space, over which again you have these notions of open sets and closed sets. Okay. But now you have to be a little careful. When I say that the set of all real numbers is closed, correct, or it's both open and closed, it is with respect to one particular metric space, and I'm assuming that the universal space is just the set of real numbers. Okay, and the distance is just the absolute value of the difference between two real numbers. Now, I think what you're trying to point out is you can view the set of real numbers as a subset of the set of complex numbers. Correct? So this lies in some kind of a smaller dimensional space. Correct? So if you view the set of real numbers within the set of complex numbers with this distance, then it is not open. Okay, it is closed but not open. So that's a good point to always keep in mind. So all these definitions assume that you have fixed a fixed metric space. So for example, when I say R is both open and closed, I mean that the space is R and the distance is just the absolute value of the difference between real numbers. Now, if I look at the set of all complex numbers and the distance being the again mod of x minus y, the modulus of the difference between two complex numbers, then in this particular metric space, R is closed but not open. In fact, not just a set of complex numbers, you can also look at R2, right? So R, the set of all real numbers, is a subset of R2. And in this space, again, R is closed, but it's not open. Here I'm assuming standard Euclidean distance. Okay, so whenever I say open sets, closed sets, I'm assuming that there is some underlying space. I'm assuming that there is this universal space. Okay, these notions of open and closed are with respect to this particular set space. So R is open and closed in R, but R is not open inside C. R is not open inside R2. Okay, and some of these will become important because when we look at higher dimensional spaces and subspaces of these higher dimensional spaces, we have to be a little careful. So if we're given an arbitrary set A and we say that this set is bounded, if you take any 2 points, then the distance is always less than or equal to some fixed value. And if I have a set, if A is a subset of Rn, is closed and bounded, so any closed and bounded subset of Rn is said to be compact. Now there's a different definition of compactness, just as there's a different definition of closed sets, but for our purposes, we will just use this. And here is a result that I will not prove, but what is most important for us is if S is some subset of Rn, in fact it can be any subset of a metric space, and so if this set is compact, and F is continuous, then the maximum exists and so does the minimum. So to see when this may not happen, let's again look at an example. So if either of these properties is violated, then potentially the minimum and the maximum may not exist. Okay. So one such example is, let's suppose that the set is not compact, it is not closed, or it is not bounded. So suppose that I have, so consider f from R to R. F of x equal to x square. Does it have a minimum? Yes. But does it have a maximum? No. Well, we say that the maximum is infinite, but in this case the maximum does not exist. Right? So this does not. So this is an example of an unbounded set. In fact, let's take the same example, but suppose my S is the open interval from 0 to 1. F of x equal to x square. Does the minimum exist? It doesn't. The infimum exists and is equal to 0. The supremum exists and it's equal to 1, but the minimum and the maximum don't exist. So this is an open set. So the sup and the inf exist, but the min and the max don't. Okay, so if the set is not compact, then the minimum and the maximum may not exist. But can you give me an example of a function which is, let's say, defined on 0 to 1, but is not continuous? And the maximum, either the maximum or the minimum don't exist. Yeah. When the supremum and infimum may exist, but the maximum and the minimum don't. So in other words, maximum and minimum are not attained. Sure, you don't even need to go to infinity. You can just take, yeah, at the boundary, so f of x equal to x square if x lies in 0 to 1, but may be equal to half for x either equal to 0 or equal to 1. Again, it seems like a sort of a pathological example. I'm just constructing an example such that some property is not satisfied. But again, you have to keep in mind that these are sufficient conditions. Right? So if these properties are satisfied, then the maximum and the minimum exist. But just because these properties are not satisfied, it doesn't mean that the maximum and minimum don't exist. correct? But for the maximum and minimum to exist, it is sufficient if these properties are satisfied. We only need to check. So this is sort of the bare minimum that we require. And our ultimate goal is to solve optimization problems, to come up with techniques that try to solve the broadest, most general class of optimization problems. So clearly, if these two properties are not satisfied, then the max and the min don't exist at all. So there's no point in looking at these. So all we need to do is add further restrictions such that we can actually solve these problems more efficiently. Okay, any questions? Good. So then let's now recall the notion of continuous functions. So suppose I have a function from, say, Rn to Rm. In fact, it can be a function from any metric space to any other metric space. But let's just take Rn to Rm. So we say that this is continuous if, can you recall the definition of continuity? So again, let's fall back to our intuition. What should happen if the function is continuous? Okay.
Take the limit of the function.
Okay.
Approaching a given point.
Okay.
Then right this side of the point, the value of the function should be the value of the limit.
Okay. So in other words, if I take any point and evaluate the function at that particular point, if I move somewhere in the neighborhood of that particular point, then the function value should not change by too much. Correct? So let's try to make that more formal. So it's continuous if for every epsilon greater than 0, you can always find a delta greater than 0, and such that what happens? I'll use the following notion, or d of x comma y. So if I take 2 points which are all close to each other, right? So I should say continuous at x. So if I consider all those points y which are within a delta of x, the distance between f of x and f of y is within an epsilon, right? Another way of looking at it is, if I take any sequence that converges to x, then then the function of that particular sequence should also converge to f of x. So equivalently, xn converges to x implies that f of xn also converges to f of x. Now that we know what a continuous function is, let's try to define the derivative. Let's look at functions from R to R. How do you define the derivative of a particular function? The derivative of f at x. Okay, so the definition you have seen is, say, f prime of x is the limit of, say, epsilon tending to 0 of f of x plus epsilon minus f of x divided by epsilon. Correct? So what does a derivative actually signify geometrically? Yeah, the slope of so the slope is essentially the slope of the tangent of the function, or the tangent to the curve at the point x. Correct? So what are you trying to do? You're actually trying to approximate your function, which is potentially non-linear, by something which is kind of linear or affine, to be more precise. Okay, so the derivative is essentially an affine representation of the function at that particular point. You can think of it as the best linear fit to the function at that particular point. So we'll define the derivative as follows. So the derivative will always correspond to some linear function. Okay. Okay, so suppose I'm given a function from Rn to Rm, so what is the derivative of f? This is going to be an m by n matrix. So if I have a function f from Rn to Rm, then the derivative of f at any point x is going to be an m by n matrix D and it has to satisfy the following property, that so this is the derivative of f at x if the limit as, say, y tending to x f of y minus f of x minus times y minus x. So this is f of y minus f of x, and this is sort of the linear approximation of the function at f at x, right? So we want this linear approximation to be close to the true function f. I'm sorry? Can you? No, the question I didn't get. You mean to say that here there is an f of x plus epsilon minus f of x, whereas this is an epsilon. So if I take epsilon approaching to 0 from the right or the left, the corresponding signs on the numerator and the denominator change appropriately. That's what you're trying to point out, right? But here the sign essentially depends on these two terms, not on the numerator and the denominator. So if you approach, let's say y, if you approach x from the left or the right, if you're looking at r, then the signs of this and this change appropriately. That is taken care of. Okay. So of course, the first thing you have to verify is that this definition also is the same as this particular definition. Both of you give the same thing in one dimension, and that's not very hard to check. So firstly, we're not entirely sure if the derivative exists, right? But if the derivative exists and it's unique, then there's a way of evaluating the derivative. It turns out that D is simply equal to the Jacobian matrix. In fact, it's slightly easier to verify, or it's easier to know whether this derivative matrix is equal to the Jacobian if all the corresponding partial derivatives, so the second order, if the first order partial derivatives are all continuous, then it turns out that the Jacobian is also equal to the derivative. And if f is, let's say, a function from Rn to R, then the gradient of f evaluated at x, simply the following vector, dou f by dou x1, dou f by dou x2, so on the vector of partial derivatives. Right, this is simply equal to the transpose of the derivative. Okay, it's important to keep the dimensions of this derivative in mind. Okay, so the gradient is going to be a column vector, whereas the derivative will be a row vector if you look at a function from Rn to R. Okay, so let's look at some easy examples. F of x equal to x transpose x. So firstly, what will be the dimensions of this derivative matrix? This is a function from Rn to R. So the derivative will be a 1 by n matrix. So the gradient will be an n by 1 matrix. And in this case, the Jacobian is simply equal to the derivative itself. So this is just the partial derivatives. So what will the gradient of f at any point x be equal to? So the first element will be 2x1. You can write this as summation I equal to 1 to n xi square. The partial derivative of f with respect to any xi is simply 2 times xi. So this is 2x1, 2x2 up to 2xn. So this is just 2 times x. Let me take another. Suppose that B is a fixed vector and I look at f of x equal to B transpose x. B is a column vector of length n. What is the gradient equal to? Simply equal to the vector B. So suppose that A is any square matrix, n by n square matrix, fixed, and I look at f of x equal to x transpose ax. What is the derivative going to be equal to? Okay, are you sure?
A plus A transpose.
2a plus a transpose. It's always easy to look at simple examples. Take a equal to say 1, 2, 3, 4. What is x transpose ax equal to? X is a vector of length 2. So in terms of x1 and x2. So it's going to be x1, x2 times x1 plus 2x2 3x1 plus 4x2, which is just x1 square plus 2x1 x2 plus 3x2 x1 plus 4x2 square, which is x1 square plus 5x1 x2 plus 4x2 square. So the partial derivative with respect to x1 is going to be 2x1 plus 5x2 this is equal to 5x1 plus 8x2, correct? So the gradient, this is in fact equal to the matrix 2, 5, 5, 8 times x1, x2, which is not 2a times x. So it will be equal to, so in general, the gradient of f evaluated at x happens to be a plus a transpose times x. Okay, as an exercise, prove this for a general matrix A, n by n matrix A. Yeah?
By brute force or like an elegant?
Brute force or
Elegant.
whatever, I mean, any method is fine. Any questions?
Transpose into that derivative.
Yes, so the transpose of this would just be the derivative.